Hello everyone, I hope you're doing well. I wanted to go through another application of differentiation with you. It's typically referred to as differentials, specifically linear approximations. And we'll do a couple examples to get the idea, but just to see how else this can be applied in the real world. And to start off, in order to talk about this, we need to recall what the symbols delta x, delta y, or just delta variable in general refer to. They represent a change for a specific variable. So delta x represents a change in the variable x, delta y represents a change in the variable y. So for many applications in differential calculus, we need to understand what a change in y is given specific values of the independent variables, so x or changes in x, for example. But this can be very difficult to evaluate, especially when you have nonlinear problems. And by nonlinear, I mean things that don't have x to the power of 1. So question is, so how can we approach such problems if we need to figure out what a change in y is for specific values in x or changing in x, whatever those represent? And we use a method of approximation to approximate this change in y that uses the derivative dy dx. In particular, we will use the tangent line as specific value of x to approximate f of x for values close to x. So in other words, say we have some sort of function, for instance, and say it's a very complicated function. Okay, so seeing, depending on what happens, if you start at this value x, and then you move over by an amount of delta x, seeing how this influences the actual values of this blue line, we can approximate that by looking at a tangent line at, say, a value x, and seeing what happens if we move a little bit over in each direction. So that's going to depend, if you move a little bit away from x, that change in the behavior of y will depend on what that slope is, so what the derivative is, and what happens when you move a little bit, a delta x, away from a specific value of interest. Assuming that that small change in x, that delta x, is not equal to 0, of course. So if we have that a derivative exists, this dy dx, then what we can say is that rate of change, this is roughly going to be equal to the ratio of what the change of y is divided by the change in x. It's like rise over run. So as long as this delta x, the denominator, is not equal to 0, then the change in y roughly can be approximated by, if you think about isolating this delta y, it would be whatever the derivative is, and then times that distance, that little change, delta x. So delta y can approximately be equal to whatever the derivative is, and then times what the change of x is. And this may seem kind of weird because up until now, we've considered this dy dx to be a symbol that represents the derivative of y with respect to x, whatever y and x represent. But what we're now introducing is a way to separate the dy part from the dx part, is to separate meanings of what they are. And then these are used to approximate a slight change in y. So doing something like that, and it may sound a little bit more complicated, I'll show you a simple example in a second, but the process is roughly the same. As you take a derivative and then you can basically separate the dy part from the dx part. When you're doing something like that, these are referred to as differentials. So let's say that you have a function y is equal to f of x, where your derivative exists. Then we have this thing that we call the differential of x. In terms of notation, we denote it dx, is an arbitrary real number, usually smaller compared to x. So delta x means a very, very small change. X is usually just some straight up number. And then we also have the differential of y. Differential of y. In terms of notation, again, this is normally denoted dy. And it's the product of f prime of dx. So in other words, these differentials, how they're connected is we would say dy is equal to f prime of x dx. Now, if you think about finding a derivative, dy dx is equal to something, you can do that, and then you could do cross multiplication to get this. But to just make sure we have a bit of a visual image, let's say we have this function y is equal to f of x. Okay, now let's say that, this is a point of interest. Okay, we'll refer to this as x here. All right, and now let me just grab this. So this point is at the value of x, and then on the y-axis that would correspond to some value, we're going to call it y. Now let's say we move over a little bit in the positive x direction and we look at another point, say up here. Okay, so say we have on our graph, I'm looking at another point, it's going to be roughly right there, and the coordinates that point is at, okay, we'll have our x1 here and our y1 here, and what we'll do is we'll call this x position will be wherever we started plus this distance that we've gone. Okay, so we're going to write this as x plus delta x, where the space in between this red line, the space in between the red line and purple line, this is the thing that we're calling this change in x, this delta x or this dx. Okay, so I've gone x plus this amount, so this purple point that I'm at, it's at the position x plus delta x. And again, we also have a corresponding y value, right? Our y value here, if we do a similar sort of thing, let's say that this is y, and now let's refer to this part right here again, that jump that I've gone, let's refer to that as delta y. So when I'm at that purple point in the y-axis, I've started from y and I've increased my position by delta y. Okay, so I have these 2 points. I have the red point and the purple point here. Okay, now let's say that I'm interested in what's happening in this function, but let's say it's just a very difficult function. Okay, and I want to approximate roughly what's going on at this point x and what happens is if I move a little bit away from it. So if I'm interested roughly at what's happening in x, we know that to see the rate of change, to see how it changes with respect to x, we can draw a tangent line, right? So let's draw something like, like this. So say I have this tangent line here. Let's see where this tangent line, so for this first red point, it interacts right here, right? But let's see how this tangent line interacts with the purple point that we're interested in. So it interacts here, and then on the y-axis, y-axis, there we go. That's how it interacts with our purple point related to the purple coordinate point. And so what we do for these differentials is this space here, the space between this blue line and then the corresponding red line. So how this purple point corresponds to this red point here. Okay, this value is the thing that we're calling dy. Okay, so what is the punchline of this picture? The punchline of this picture is the more the dx here goes to 0, it means that this dy is going to approximate this dx, because as this goes to the red line here, that means that this cyan color is going to go to the red line. So our dy would be approaching delta y. So for a small non-zero value of dx, what do we have? We have that dy is approximately equal to delta y, or in other words, dy is equal to f prime of x dx. So this is the picture that kind of goes along with differentials. And this may still be kind of confusing. So let me show you a quick example. Okay, so say that I want to find my differential dy of the following function, and I want to see what that change of y is if I'm taking x to be 10, so I'm at the point 10, and my delta x to be 0.01. So if I'm 0.01 away from the x value of 10. So you would just differentiate this function normally. Okay, so what is the derivative of y? Well, we're going to write as dy dx is equal to, by power rule, I have this as 12x. And so differentials, the definition, what it means is that what I can do is I can separate the dy part and the dx part, okay? Because this generally represents just a change in y over a change in x, rise over run. So I can cross multiply and isolate for my dy to give me 12x dx. So then, if I'm considering these specific values of 10 and 0.01, my dy is going to equal to 12 times 10 times 0.01, which will give me 1.2. Okay, so basically the concept of a differential is you differentiate as you normally would, but then we think about separating out the change in y part by the change in x part. And as mentioned, differentials can be used to approximate function values for given x values. So notice that if I'm looking at this change in y here, this delta y, what is this gap here? How would I find it? Well, I would go this purple line minus this red line. And what does that correspond to? Well, this is f at the point x plus delta x, and then minus f at x. So that delta y, what it's actually equal to is whatever the f is at x plus delta x, subtract f of x. Okay, so for some small but non-zero value of delta x, our change in y is approximately equal to this dy, so that this expression that we found here, that change in y, it's roughly equal to our dy. Or in other words, if I want to isolate for this part of the equation, the f of x plus delta x, we can think about that specific term as being the change in y plus f of x, and that will give us this expression here. But what is our dy? We saw before that dy can be written as f prime of x dx by doing cross multiplication. So if we're trying to see a function, what it is at x, but then what it is a small distance away from x, this can be approximated by whatever the function is at x itself, and then plus its slope, its derivative, how it's changing, its rate of change, times dx here. This expression right here, this is called the linear approximation. And this can be used in many health science applications, but it can be also used just in mathematics in particular. So let me show you an example of where we just use this in general mathematics and then an application where it can be applied to in life sciences. So say I don't have a calculator and I want to approximate the square root of 50 using the linear approximation. Okay, well, what exactly does that mean? How do I do that? So if I think about, okay, I have this f value, I want to know at a particular point, I can approximate it by the function at an x value, plus how it changes a little bit over a small change in x. In this situation, what we can do is we can think about the function that we're interested in is the square root of some number x, which would mean that its derivative would just be 1/2 x to the negative 1/2, because we can write this as x to the 1/2 and just use power rule. Now, what is the square root of a value that we know that's pretty close to this? Well, we do know what the square root of the square root of 49. I know what the square root of 49 is. That's just equal to 7. But what do I want? I actually want the square root of 50. And 49 is just 1 away from 50. So if I think about the change in x, the distance away from something that I know is just being 50 minus 49, then for a situation like this, we think about this little jump here in x as just being 1, okay, which is equivalent to saying, my dx would be equal to 1 in this situation. So when I'm looking at this linear approximation here, it's going to be approximated by what the function is at a point that I know, plus its derivative at the point that I know, and then that little change in x. So in our case, we know what these things are. My f of x is just x to the power of 1/2. I know that the derivative of that is 1/2 x to the negative 1/2. And then I have my dx here. So if I substitute, okay, the thing that I know, f that I know at 49, that's my x. And then the change in x, how far away I am from something I know is 1, what this will give for our linear approximation is the following. Is my head in the way? Not quite. So I know what happens at 49, which is 1 away from where I want to get to. Okay, and so f at something I know, 49, okay, that's fine, plus the derivative at 49, but I am 1 unit away from where I want to be. Okay, if I simplify this, the root of 49, this is 7. Over here, this is going to end up giving me 1/2 times 1/7, so that's 1/14. So f at 50, I'm approximating it by the 7 plus 1/14, which is roughly equal to, if we throw it into a calculator, 7.07143. Now, if you plug into a calculator, what is the square root of 50? We get 7.07107, which is pretty good, right? After the decimal, the first 3 are lining up here. Okay, so this is an example of, I have some sort of a function, square root of 50, I don't know what that is off the top of my head. So we work with something that we do know. We see how far away we are from what we want to get to, and we can use this linear approximation, this expression that depends on what the function is at the point that we know, and then what happens if you move a little bit away from it, okay, the derivative, that tangent line. Okay. So let me show you a life science example of where this can be used. And we're not going to focus very much on this in this course, but when you start applying some of these things into upper year, you may end up using this approach. Okay, so let's say that researchers have observed that the weight of a male pig can be estimated by this equation. Okay, researchers have this equation where T is the age of the boar or the male piglet in days, and the WT is the weight in kilograms. So if a particular boar is 70 days old, okay, we want to estimate how much it'll weigh when it's 73 days old. That's pretty difficult overall, but we can use differentials to find that approximate change in the pig's weight resulting from those extra 3 days. Now, how could we do this? So the change of the weight can be approximated by, well, a small change in weight, that's what dW means here, is equal to the general rate of change, and then depending how much the time difference is that we're looking at. Okay, so W prime of t dt, where the t in our case, we know what happens at 70 days. So I have an answer at t is equal to 70. That change in days, the number of days I want to consider the pig's weight as change after is 3. So my dt in this case would be 3. So I know how to actually find the derivative of that function. The derivative of the first term here, this is a constant, so that would be 0. And then I have my 160.1. This is a very beautiful function, e to the power of e to the power of stuff with t. So it's still just an exponential, so we're going to rewrite what we have. So I have e to the power of negative e to the power of negative 0.0212, and then this is times t minus 103.63. And then when you're doing derivative rules, so you rewrite what you have, and then you take the derivative of the thing in the exponential. Well, if I just pretend this is not here and think about taking the derivative of this, I have to rewrite what I have again, right? So minus e to the minus 0.0212 times t minus 103.63. And then I have to take the derivative of this top part. So I have a constant times t plus a constant term I ignore. And the derivative of this constant times t with respect to t is just going to be negative 0.0212. 0.0212. There we go. And then I have my times dt here. So times dt. Okay, and so now what we're going to do is we know what happens on the 70th day. I'm curious to see what happens with the change of t of 3 days. So in order to get my change in weight, which is approximately equal to this dw that I have right here, what I'm going to do is take my expression, okay, that I have here. So the 160.1 multiplied by all this absolutely gorgeous stuff here that I'm going to copy and paste because I'm able to. We're going to change our t's to 70. Okay, so I have 70 here. I have a 70 here, and my dt, okay, I'm curious in what happens after 3 days. Okay, so I can multiply 160.1 by this by 3 and then by negative 0.0212. Okay, so that will give me a negative number. And then I have another negative here, so that will become positive. And if I actually plug these e's into Google or to a calculator, I will approximately end up getting 2.70. All right, so that's nice, but what does that actually mean? So what this means is therefore, or thus, a 70-day-old boar is expected to grow approximately this much. So what is that? Our stuff is in kilograms, so 2.70 kilograms during the next 3 days. Okay. So here's a mathematical example of, how you can use the linear approximation to approximate specific numbers, so numbers in certain functions. For this one, it was the square root function, and little things like looking at little changes in certain variables, and if you need to do linear approximations. Okay, so again, we're not going to be spending very much time on this at all, but it's just to show you another application of how derivatives can be applied. Thank you.